Today, I'd like to present an analysis of the Bayesian hypothesis for visual-vestibular cue combination. The topic is the control of locomotion through the 3D world. For locomotion through the world in which we operate, a core issue is the coding of its 3D structure through the neural computation of the multiple depth cues and their integration to a unitary representation of the changing scene. To assess performance with multisensory cues, we may consider the perceived heading from motion in depth conveyed by visual and/or vestibular cues. The data for the analysis were kindly provided from a behavioral study with monkeys published by Docker, DeAngelis, and Angelaki in 2015. The perceived heading was biased by an auxiliary cue of the lateral motion of a visually defined sphere with a juice reward for a correct response as to whether the physical heading was to the left or right. The individual heading estimates were substantially biased by the decoy sphere motion for the visual and vestibular cues alone, but much less so when the cues were combined. Theoretical distributions for the present Bayesian analysis were derived from the individual trial data. This is a classic example of the visual information for heading from optic flow. Here the optic flow field is generated by travel on a straight path, with the focus of expansion on the horizon, from Gibson, 1950. Note that this is a purely visual display from the pilot's viewpoint, so the distance scaling depends on the pilot's cognitive scene understanding. Now that was just one individual space cue. Here I want to revisit a scheme I developed a while back for the integration of multiple space cues. The first part of the diagram concentrates on the various binocular disparity cues from position, stereo motion, orientation, and so on. Once these are integrated together to provide a dynamic depth structure, they have to be combined with the proprioceptive and monocular space cues to provide the overall percept of 3D motion that tells us which direction we are heading in. Now, in the study under consideration, the monkeys were housed in an elaborate apparatus consisting of a capsule with a 6 degree of freedom motion capability to produce the vestibular heading signals, together with back projection of the visual motion information for the 40-degree flow field and the decoy motion of the ball. So here's a simulation of the kind of visual information presented to convey the heading signal to the monkey, with the decoy motion of the ball to the right. I'll play that again to give you a second look. So here are the distributions for the measured visual heading settings for one monkey, named Quigley, under the no decoy control condition. The monkey had to set straight ahead with motion simulations over a range of plus or minus 20 degrees of heading angles. The format is that the visual flow field was presented at 3 levels of coherence of the noise: low coherence, high coherence, and an intermediate level set to match the heading accuracy of the vestibular performance. When the decoy was added with leftward motion, the derived heading distributions both became substantially broader and showed a rightward bias to compensate for the leftward influence of the decoy motion. Conversely, the rightward decoy motion induced the opposite shift to the left. Here the added blue curves show the settings for the vestibular motion, alone and with the decoy motion of the ball, in the same format. Curiously, for this monkey, the leftward decoy induced similar compensatory effects as for the visual flow field, but the rightward decoy settings were almost unbiased and somewhat narrower than without the decoy motion. This is an idiosyncratic example of the range of behaviors that could occur across the group of monkey participants. So those are the data. Here is the logic of the obligate Bayesian prediction for the combination of the heading distributions for the two cues. The general assumption is that combining cues among modalities will enhance performance due to correlated signals and uncorrelated noise. In depth perception in general, we are typically unaware of the wealth of cues contributing to the final result, implying that the cues are automatically combined in a relatively optimal fashion. This obligatory form of cue combination may be disadvantageous if some cues contain distracting or distorting information. To calculate the combined prediction for the present heading paradigm, we have to remove the double effect of the decoy motion from the combination of the individual results, since the effect of the decoy alone was not measured. So, the theory is that the combined distribution is equal to the product of the visual, the vestibular, and the decoy distributions. For the data, we have the visual alone, the vestibular alone, the visual plus decoy or times decoy, the vestibular times decoy, but no decoy alone. So to calculate the prediction for the combined distribution, we need the product of the visual plus decoy condition and the vestibular plus decoy condition divided by some measure of the decoy condition alone. This can be obtained by multiplying the four measured conditions, the visual alone, the visual plus decoy, the vestibular alone, and the vestibular plus decoy, and taking the square root of that product. This procedure achieves the result of generating the prediction of the product of the visual, vestibular, and decoy alone conditions as theoretically required. Those predictions for the combined heading distributions are shown as the red curves for the no decoy, leftward decoy, and rightward decoy conditions in the same format as before. So the acid test is how well those predictions compare with the measured heading distributions for the combined visual and vestibular cues, shown here by the green curves. Although they are not too far off for the no decoy and rightward decoy conditions, the empirical distributions show much less bias than the obligate Bayesian predictions for the leftward decoy conditions, plotted in the center column. Now, those were the derived distributions for one individual monkey. The average estimates for the whole group of 6 monkeys can be summarized in terms of the distribution parameters, here for the distribution means, or average heading biases, at each coherence level. The biases were small for the no decoy conditions, with no significant differences between the theory and the result. When we come to the leftward decoy condition, you can see that the group as a whole was strongly biased in the separate Q conditions, giving the biased prediction of the red curve, but much less biased in the measurements for the combined condition, shown by the green curve. This result was replicated in the other direction for the rightward decoy condition, showing that overall, heading biases are significantly lower than the obligate Bayesian predictions. Now, if we switch focus to the usual parameter for Bayesian analysis, which is the spread of the heading distributions, or sigmas, we see that the obligate Bayesian predictions fare no better. The standard deviations of the combined distributions are much lower than the predictions, at about 1 to 2 degrees of heading variability, rather than 2 to 4 degrees for the predictions. To overcome this problem, we can consider an optimal selective attention strategy. Since the distractor motion of the decoy ball is only in one modality, the visual, can the monkeys improve their performance by selectively attending to the least biased heading cue on each trial? This strategy would help to avoid the influence of the decoy motion at the cost of the Q combination advantage. So the notion here is that the combined response is derived from the least biased of either the visual or the vestibular cue when presented in combination with the decoys. However, this theory requires the assumption that the monkeys have access to some standard of zero bias, which could be provided by the physical structure of the capsule in which they are installed. This strategy produces the highly satisfactory result that the predicted values for the combined Q distributions are much less biased and in fact are not significantly different from the measured biases. This result indicates that optimal selection of the heading Q gives an accurate prediction of the measured biases for all three sets of conditions. Again, a similar result is obtained for the distribution sigmas. The predictions come down to the range of the measured sigmas of about 1 to 2 degrees. And so to my conclusions. In summary, the monkeys were quite accurate, as may be expected from their lifestyle of swinging through the trees with tigers lurking down below. The surprising result of less bias with the combination of two biased cues was incompatible with the obligate Bayesian account, but could be explained by a selective attention hypothesis. And thanks again to Greg, Kalpana, and Dora for giving me access to the detailed data from their impressive study of monkey heading psychophysics.